Hey there, and welcome to the Factorial Analysis of Variance module. In this video, I'm going to give you an overview of all the different resources available in the Factorial ANOVA module and go through a brief lecture on Factorial Analysis of Variance. As with all the modules, always start with the README file. If we click on it, it'll take us here. It gives you the different assigned readings for the week. You know, what chapter in the textbook will follow. If you're not using the Gravity and Walnut text, just look for two-way analysis of variance or factorial analysis of variance chapter. If you need help, just let me know, and I'll help you find it in your book. There's my lecture notes, an example of using two-way ANOVA and SPSS, and then a little write-up on different post-hoc tests. You can also download a zip file here with all of the non-textbook readings, so all of these, and then some additional optional readings if you want to learn a little bit more about Factorial ANOVA. You can also, there's that zip file there too of all the readings that aren't in the textbook. Here are my notes on factorial analysis of variance. We'll come back to this for the lecture part. We'll follow along with this. Below here are examples and SPSS walkthroughs. Here's a link for, it's a document with steps for running a factorial analysis of variance in SPSS. If you click on it, then it has, a step-by-step guide of how you'd run a factorial analysis of variance in SPSS, and if you have a significant interaction effect, how you do the simple main effects analysis. I've made separate SPSS walkthrough videos for if you do not have a significant interaction effect, how you would interpret a factorial ANOVA in that case. Here's the walkthrough video. Here's an example. Here's the data set, the SPSS data set that goes along with that example. And here's an example write-up from this example. So it'd be like an example results section. You can see. Here's all the same stuff, but what we would do if we had a factorial ANOVA and we have a significant interaction effect. Here's my video walkthrough. If you click on it, it should bring you to, if it doesn't show up in here, just click on the link at the top and it'll bring you to the YouTube page there where I'll walk through the analysis for you. So there's the example I go through, and then all the examples have the research scenario. We'll open it up and we can see. You can see it has the research scenario here, how you'd run it in SPSS, what the data look like in SPSS, and then the annotated output, what we're looking at, how we interpret each one of these tables, what we would do, so you can see the output being annotated there. As I said, there are separate videos walking you through each one of those, so I'm not going to do that here. This is a 2-week module, as you can tell from the dates here at the top. So for the first week, we have a discussion post due. So we have a discussion post on factorial ANOVA. So if we click on this link here, it'll take us then to the discussion post. So for this week, we're going to critique an article that uses factorial analysis of variance. You can click on this link or this one to download the article. You could view it in here too if you wanted to. And basically what I want you to do is to critique the write-up of the results section. Basically, was the write-up of the analysis clear? Did the author provide all the relevant information for the analysis? Were table or graphics used in the analysis? Were they useful in helping you interpret the results? did the authors provide further explanation of the results in the discussion section? Is there anything you would have done differently? Any other analysis you may have conducted to help, explore this area? I want you to read the article and provide a critique. Try to keep the critiques, fewer than 500 words. I don't want these to get out of hand. And then post your critique to the discussion board here. So then we can see what other people found here. Maybe other people caught things you didn't catch. So it'd be interesting to see. It's interesting to see what everybody else gets out of the article as well. So this is what we're going to do, our assignment for the first week. And then at the end, by the end of the 2 weeks, you have a data analysis assignment and a quiz like we do every time. Here's the data analysis assignment. You actually have 2 problems. This time one we're going to have a factorial ANOVA without an interaction effect, and another one's going to be a factorial ANOVA with an interaction effect. So you can see the research scenario here. Here's the data, so you'll enter these data into SPSS. Notice on each one of these, I gave you, once you have the data entered into SPSS, you could run just descriptive statistics on your dependent variable for the overall heart functioning and make sure you get this value. That'll help you to know whether or not you entered your data incorrectly. Instead of typing in a 53 here, you type in a 35, then your average here would be slightly different. So it's kind of help you, kind of clue you in to make sure you've entered the data in correctly. Same thing here. Here's your example scenario. Here is, here's your data and enter into SPSS. And here's the overall mean for the average amount of sleep for all 36 subjects. So you can make sure you entered your data in correctly. And, the analysis should follow along, very similar to the 2 examples that we have in class here as well. One of them will be a 2-way ANOVA with no interaction. Another one will be a 2-way ANOVA with an interaction. All right, so now that we know, kind of give you a little overview of all the different material that's out there on Canvas. Let's look at the notes on factorial analysis of variance. Just give us, we'll just talk through a little overview of factorial ANOVA. Open these. So, these notes are intended to kind of help you supplement the readings and kind of really hit the high points of the readings. And then you can go back into the readings and get more detail here. So for the factorial between subjects analysis of variance, here we're going to have more than one independent variable. So this is basically an extension of the one-way between subjects analysis of variance. Instead of just having one independent variable, we're going to have 2 or more. All the examples I'm going to give you are going to be 2-way between subjects ANOVAs, but you could also have 3, 4 ways. They just get a lot more complicated, but all of the stuff is basically the same with the higher level ANOVAs as well too. So here's some key concepts to kind of keep in mind. The big thing we're going to talk about here are interaction effects, which I think will be new for you, and then whether the interaction effect is significant or non-significant then affects the type of follow-up that we'll do. And so we'll talk about that a little bit in these notes here. So in a 2-way between subjects ANOVA, we have a single dependent variable right? Our dependent variable is usually continuous or measured on an interval ratio scale. And we have two independent variables here. That's why it's called a two-way analysis of variance. A lot of times we call these independent variables are called factors in an ANOVA sense. That's why it's called a factorial design. And then, usually we'll talk about these. So if one of our independent variables has two levels, the other independent variable has three levels, we might call this a 2x3 factorial design, and we'd write it by here like 2x3 factorial design. So it's just saying that one independent variable has two levels, the next independent variable has three levels. One advantage of a factorial design is that it allows you to test whether levels of your independent variable affect the dependent variable the same way across levels of your other independent variable. And that's what we call an interaction effect, whether the impact of variable A on our outcome depends on the different levels of independent variable B. Might make a little more sense when we talk about some examples here. Another advantage of a factorial ANOVA is that it controls more error variance. That's what we're trying to show here. And like a one-way ANOVA, we have the explained variance or the variance between groups, and then we have the error variance, which is unexplained or with the within group variability. With a two-way ANOVA, we can eat up more of that error variance in a sense. We'd have variance explained by our first independent variable, variance explained by our second independent variable, and then variance explained by the interaction between our two independent variables. And so that's kind of what these are supposed to graphically show here. Three of the main reasons why you'd want to run an ANOVA. You want to test two independent variables simultaneously, right? It's more efficient to test two factors at the same time rather than two separate one-way ANOVAs. We just talked about that smaller error variance piece by including that second factor that we think influences our outcome. We can explain more of the error variance in there. And we can also have an interaction hypothesis, what may be of interest. Does the effect of one variable depend on the different levels of the next, of the second variable? Here just presents the summary ANOVA table. I'm not going to have you calculate a one-way ANOVA, a two-way between subjects ANOVA by hand. This is just kind of how you would calculate it. One thing you should notice here is notice that there are 3 F-tests reported here. That's interesting, huh? There's an F-test for the main effect for our first factor. There is a significance test or an F-test here for our second factor, and an F-test for our interaction effect too. So we have 3 separate hypotheses tests in the two-way ANOVA. So what we would call factor A and factor B here, these 2 tests will be tests of the main effects. So what is the effect of factor A, basically averaging over all the different levels of factor B? And then this test would be what's the effect of factor B on our outcome, basically averaging over, ignoring differences in factor A. And then our interaction hypothesis here would test whether the impact of factor A on our outcome depends on the different levels of our factor B variable. So for the example I give here, so we're interested in examining the relationship between teaching method, gender, and math achievement. So math achievement would be our dependent variable or our outcome, and our two independent variables would be teaching method, say like teaching method A and B, and gender, whether the student was male or female. So an interaction hypothesis would be that the impact of teaching method on math achievement would depend on whether the student was male or female. So maybe method A is better for females and method B is better for males. That would be an interaction effect. So, you know, which teaching method is most effective for improving math achievement? Well, it depends on the gender of the student. That is what would represent an interaction effect. We'll go through another example in the notes a little bit more. Excuse me. So we have some effect sizes for our between subject designs. So yeah, our effect sizes, we'll get a main effect size for the entire model reported in our output. That will be reported, the SPSS will call it R squared and adjusted R squared. Here are the formulas for how it does it. And so it's basically the proportion of variance in our outcome. So if we're using this math achievement, gender, and teaching method example, it would be the proportion of variance in math achievement that's explained by the teaching method, the gender of the student, and the interaction between teaching method and gender. So that would be like an overall eta squared or R squared, using regression terminology, for the entire model. SPSS will also give us partial eta squareds for each effect. So we'll get a partial eta squared for teaching method, which would say, you know, X% of variation in math achievement is explained by the different teaching methods. We'll get another partial eta squared for gender, which would be the proportion of variance in math achievement that's explained by differences between males and females. And you'd get one for the interaction effect too, which would be the proportion of variance in math achievement that's explained by the interaction between method and gender. Partial eta squared tends to, and eta squared, both of these tend to overestimate the proportion of variance explained in the population. And so usually there's an adjustment made. That's what the adjusted R square does for the overall model. And omega square does that for the for each of the individual effects. SPSS doesn't calculate omega square, so you'd have to calculate it by hand, or you could just report the partial eta squared and note that in your write-up. That's what you're reporting. So the assumptions from the factorial ANOVA are the exact same as they were for the one-way analysis of variance. You know, we have an independence assumption. You know, the observations from each sample are independent of one another, or the observations from each sample don't depend on observations in another sample. You know, we assume that the dependent variable is normally distributed in each one of the populations. You know, ANOVA is generally robust against this assumption, so violations of it are kind of minimal, especially as your sample size gets larger, thanks to the central limit theorem. And then we also have our same assumption of homogeneity of variance, that the populations from which the samples were drawn have equal variance. So we're going to report and test this. You know, violations of the assumption are the same as it was in the one-way case. And then it kind of follows the same rules of thumbs too. If you have equal sample sizes or approximately equal sample sizes in each of the groups, then violations of the assumption aren't severe. So now for our new term, interaction effects. So, a significant interaction effect tells us that differences in the dependent variable depend on both independent variables. So, any changes across levels of one independent variable will depend on what level you are on the other dependent variable. So back to that math achievement, the teaching methods, and gender, that if there's a significant interaction effect, it's saying that the impact of teaching method, which teaching method is most effective in increasing math achievement, will depend on the gender of the student. So, teaching method A may be more beneficial for females, and teaching method B may be more beneficial for males. That would be an example of an interaction effect. When we have a significant interaction effect, we're not going to interpret the main effects. What we're going to do is we're going to ignore the main effects and run what's called a simple effects analysis or a simple main effects analysis. And if the interaction term is not significant, then we'll interpret the interaction effects. It doesn't make sense to interpret the interaction effects. Like, it doesn't make sense to interpret the main effects for teaching method or main effects for gender when there's an interaction between the two. So here's another example here. Suppose a researcher is comparing two different methods of science instruction and want to know if the science instruction depends on the gender of the student. So this is very similar to our example above. So 25 females and 25 males are randomly assigned to be taught a lesson on weather patterns using method 1 or method 2. And then after a set amount of time, they're given a proficiency test on weather patterns. And suppose these are the data that are presented. So if we ignore the interaction between gender and teaching method and just interpret the main effects or these marginal means over on the side, if we look at the marginal means of males and females, it looks like there's no difference, right, between males and females, in their proficiency of weather patterns. If we look at the main effects here for the different teaching methods, it looks like method 1 is superior to method 2. So if we ignore the gender of the student, method 1 looks superior to method 2. However, if we know the student is male and we look at the differences between the teaching methods, it looks like method 2 is superior for males, which is different from what we found with the overall means. Right? If we look at females, it looks like method 1 is clearly superior. So this is an example of an interaction hypothesis. The marginal means or the main effects may be a good explanation of what's going on overall, but doesn't tell you what's happening across levels of the other independent variable. It looks like method 1 is superior overall, but if we look at the effect just for males, it looks like method 2 is superior for male students and method 1 is superior for female students. So significant interaction effect usually reflects a situation like this. Overall estimates may be fine for the average performance, but won't necessarily be true for information within each level of the independent variable. Usually what we do when we find a significant interaction effect is we like to graph then the interaction effect. And that's what, can I show them both on here? Whoops. So you can kind of see that's what I have. These four figures are kind of example interaction effects. So we could think of, you know, the different lines as being males and females, and this being our different teaching methods, although we have three of them here in this example. Figure A and B would be illustrations of no interaction effect. Usually no interaction effect is illustrated by parallel lines, or each line segment is parallel, is what we see here. This would be an indication of no interaction effect. We see like similar differences across, so say these are teaching methods, this is males and females, we see similar differences between females are superior to males across each level of our teaching method. Same thing here. Teaching method 2 wasn't as effective for both males and females as teaching method 1 or 3 were. Figures C and D here would be example interaction effects. It's when the line segments aren't parallel, typically indicates, is how we typically would see in a graphic that would indicate an interaction effect. When the lines cross, you might hear it called like a disordinal interaction. And when the line segments don't cross, you might hear it called an ordinal interaction. But both of them would indicate some type of interaction effect. Like if we're looking at mean differences here for teaching method 1, say we probably wouldn't find a significant difference between males and females. For teaching method 2, we probably would find a significant difference between males and females. In teaching method 3, we wouldn't find a significant difference between males and females. Whereas with the parallel lines, we come to the same conclusions each time. Same thing here. You know, we might find a significant interaction, you know, a difference here, but no difference here, no difference here. You know, it looks like for males, you know, females are scoring higher than males on both teaching method 1 and 2, and then 3, they flip. That's another indication of a significant interaction effect. So basically, the first things to do, like kind of our first rule of thumb, is when we run a factorial between subjects ANOVA and the interaction term is not significant, basically then we can then interpret the main effects. We would interpret these marginal means here. We'll interpret the main effects in the table and run post hoc tests on any of the main effects that are statistically significant, especially if there's 3 or more groups. If we have a between subjects factorial ANOVA and the interaction term is statistically significant, we're going to ignore the main effects. We're going to plot the cell means and run a simple effects analysis. So here's an example of a simple, we plotted the cell means. This is using the example of the two-way ANOVA with interaction effects. We were looking at the differences in 3 teaching methods for students with, I think we were looking at mathematics achievement for students with high reading ability, average reading ability, and low reading ability. So this would what the cell means for each one of those groups would look like. What we'd probably expect to find here is that there is no difference in the 3 teaching methods between the high ability group. It looks like there's probably no difference in teaching methods for the average reading ability group, but it looks like there's definitely a difference in teaching methods for those in the low ability groups. That'd be an example of an interaction effect. So yes, before you plot the cell means, you have to decide, which group you want to run your simple effects on. I'm going to tell you in the assignment how I'd want you to run the simple main effects analysis. So for the plot above, we're looking at differences between teaching methods here. Here we're looking at differences between teaching methods within each reading ability level. And then in this plot, we're looking at differences in reading ability levels within each teaching method. So here we're comparing the average math achievement scores for students who were taught in method C, who were in the low, middle, and high reading ability levels. So you could run the simple effects analysis either way. Basically what the simple effects analysis does is you're basically selecting on one of your independent variables and running a one-way ANOVA within each level. So what we're doing here is we're going to look at only those in the high ability group and run a one-way ANOVA comparing the different teaching methods. We'll look at another one-way ANOVA comparing, looking at the one-way ANOVA, only looking at those in the average ability group, and run a one-way ANOVA comparing the different teaching methods. We'll run a third one-way ANOVA comparing, looking only at those in the low ability group, comparing the three different teaching methods. So that's what the simple main effects analysis is. We select on one independent variable and compare levels of the other independent variable within levels of the other variable. So here, in this analysis, we are selecting on teaching method and comparing the different ability groups across each other. So for those who were taught with teaching method A, is there a difference in the low, middle, and high ability group? Same thing with teaching method B and teaching method C. That's what we're showing here is the simple effects analysis. So following a significant interaction, we need some procedures to explain that interaction. And so, the simple effect is really the effect of one independent variable within levels of the second independent variable. So what's the effect of teaching method for high ability students, right? It doesn't look like there is a difference in teaching methods for those in the high ability group. Is there a difference in teaching method for those in the middle ability group? It doesn't look like there's probably a difference in teaching methods for those in the middle ability group. But it looks like, yes, there is a difference in the different teaching methods for those in the low ability groups. It looks like methods C and B are superior for those in the lower ability group than method A. So that's what our simple main effects analysis would do. And so that's what it's showing here. See how it's comparing these different cell names. We'll work through this example in the two-way ANOVA with interaction effects. I go through this example for you. And there's also an example demonstration of how we'd run the analysis and interpret it in SPSS for a two-way ANOVA without an interaction effect. Also linked in here are some other helpful videos, other videos you might find helpful. They're all linked in the notes documents as well. And don't forget the video walkthroughs of Factorial ANOVA no interaction and Factorial ANOVA with an interaction videos there too. And as always, if you have any questions or concerns, please email me, post to the message board. I'm always here to help. Thank you.